So here's an example, an interesting example, and it's in the textbook, but you can have a, so you could have a look at it in there, but let's look at it anyway. On the face of it, it looks pretty straightforward, and you might rightly suspect that I'm going to have to use integration by parts to do this, because x appears twice. I've got two functions, x on its own and log x. And up till now I've been thinking the bit I'm going to call u, I'd like that when I differentiate it to disappear. And if I differentiate x, I get 1. So I will be very tempted to let u equal x. So therefore dv will have to equal log x. And then I'll look at my table of standard integrals and find that that's not on there. There is no integral of log x. So, oops. Okay. What we actually do is we do it the other way around, because if you look at your table of differentials, the differential of log x is 1 over x. So actually that's the way to go in this particular example. So if I've got natural logarithm functions in here, it tends to be, I'd probably call that u. So in this particular case, that's what I'm going to do. I'm going to let u equal log x and dv equal x. So with u equal to log x, I'm going to differentiate that, and with dv equal to x, I'm going to integrate that to get v, differentiate this to get du, and then substitute those in and go from there. So have a go. So if we try it, u by dx equals 1 over x. Yep. So well, first of all, differentiating u, looking at our table of differentials, differential log x is 1 over x, so that's where that comes from. This one, the table of integrals, this is the standard integral, and the standard integral I'm using is the integral of ax to the n goes to ax to the n plus 1 over n plus 1. That's the one, isn't it? So I'm just adding 1 to the power of x, which gives me x squared, and then dividing by the new power, gives me x squared over 2. So now just substitute those in. Using integration by parts, the integral of u dv equals uv minus the integral of v du. So substitute those values now for u and v and du and dv into there and work out the solution. No, we're not using algebraic substitution. So all we're doing is saying, I'm going to now, in here, when I see du, I'm going to use that. Yeah. So I'll pause that, and then we'll carry on in a sec. So plugging in values, we get this. That our integral is that. So our original integral, which was this, is now replaced by the bit on the right hand side. And we can tidy this up, which means we can do it. That's okay. So that's, I would probably just write the x squared over 2 first, and then the log x minus. Now if we look here, that x cancels with one of the x's here, so we're just left with the integral of x over 2 dx. And that's a standard integral. Remember, we can think of this, we didn't necessarily write it as minus the 2 underneath is like multiplied by a half, so divide by 2 is Andrew is saying is the same as multiplied by a half. So take the half outside the integral and you're just left with the integral of x, which is just x squared over 2. So we end up with a half times x squared over 2 plus c. And that's our answer. We can tidy up and we can factorise that. Try and make it look better. We can multiply that half by the 2 here. And then we can think about taking common factors outside, factorise outside a bracket. So just try doing that, tidy up. So I can, there's a couple of ways, I can times the 2 by the 2 to get the 4 here underneath, but actually probably better would just go jump straight to this, because I can take a half x squared outside the bracket, leaving log x minus a half inside the bracket plus c. Okay, I'll stop that there.